So thank you, Enrique, and all the organizers. It's been such an interesting conference. So today what I like to talk about is quantum machine learning for quantum anomaly detection. And before I sort of start with the anomaly detection, maybe let me just speak a few words about sort of the motivation, how this work kind of came about. So my main interest is at the intersection between security problems and computation. So security and quantum computation. Things like delegated quantum computation, blind quantum computation, verification quantum computation. And actually that's the subject I spoke about when I was in Bilbao last month. And in these questions of involving security, they become more important when quantum devices become more prevalent. So we have access not only to one, but multiple devices. And in these kinds of cases, we have multiple devices communicating with each other and maybe even collaborating with each other. And of course, in these kind of network cases, we also end up having security problems. And one of these problems are things like when you have intruders or eavesdroppers. And you need to consider these adversarial type of scenarios. And in classical networks, there's a problem that comes up, which is called anomaly detection. So what exactly is an anomaly? It's some form of irregularity to a pattern that you expect. So to show you, you sort of already know what anomaly detection is. Okay. Right. So these are lashes. These are a breed of domestic sheep that's native to the Basque Country. And when you look at it, you sort of have a basic idea. Next time I show you lashes, basically what they are. These big, fluffy white sheep. But then some of you might have noticed that there is these kind of odd guys in the picture, and you notice that these are odd guys without me telling you, to look for these black sheep. So and by doing that, you've just performed classical anomaly detection with a classical device, on your shoulders. And so what we like to do is, we know that in classical anomaly detection, it's an enormous field in its own right, and machine learning has been a very important tool in classical anomaly detection. But when we think about quantum devices and communicating quantum devices, then they're sending each other not only classical bits of information, but also quantum data in the form of quantum states. So the basic idea behind this work is to say, if classical machine learning is useful for classical anomaly detection, then perhaps quantum algorithms, quantum machine learning, might be more natural setting for anomaly detection for quantum states. So that's what the two quantums are in the title. But just like the no free lunch theorem in classical machine learning, there's no single algorithm that works best for all situations. The same is true for anomaly detection. There's no single anomaly detection algorithm that should work for all types of anomalies. And not only all types of anomalies, but there are different situations in which you might find anomalies. But broadly speaking, there are about 6 classes of algorithms that people have been looking at. And you can see, on this list, most of them are actually based on machine learning type of algorithms, classification-based, spectral-based, nearest neighbor, and clustering-based. And a lot of these algorithms we already heard of throughout this week. And there are also statistical techniques, things like, you might assume your data to have a Gaussian distribution, and any deviations from that, you might call it an anomaly. So we also have, non-machine learning techniques, but most of them are based on machine learning, and they've been very successful. So some of these algorithms which you might use when your computer used to detect credit card fraud, right? These are based on these machine learning anomaly detection algorithms. Okay, so why are there so many different types of machine learning algorithms? So there are different types of anomalies, and the general class are point anomalies, contextual anomalies, and collective anomalies, and different situations in which you might find anomalies. And in this case, you need supervised, unsupervised, and semi-supervised. And I'll go through these briefly in turn. So first, point anomalies. So what do I mean by point anomalies? So imagine a case you have a collection of photographs of healthy lung tissue. And you plot these in your feature space, and you say, this is kind of normal. What we call normal data. And then you're given just one more piece of test data, another picture of a lung tissue. And you ask, is this normal or not? if it's not normal, maybe it has emphysema or something. And then so this is a point anomaly. And then we have contextual anomalies. So this could be the graph of temperature here in Bilbao. And we notice here in March, there's a bit of a spike. But it's not anomalous in the sense of the value of the temperature itself, because it's just a little bit higher than July. But in the context of March, it's anomalous. And these occur a lot in time series type of data. And it occurs, it's very much related to the change point problems that Ramon and talked about on Tuesday, so Ramon and Gail's work. And then we have collective anomalies. So this is when it's the collection of data themselves that together form the irregular pattern, something that breaks the symmetry of your regular pattern. Okay, so, and then there are three situations in which we might find anomalies. So one, supervised, meaning that we have our labeled data, which we call normal, but also labeled data, which we call anomalies. So if you're looking for a specific type of anomaly, like a particular type of spam, right, then you have a lot of data on what is anomalous email. And then you can use your favorite supervised machine learning technique and separate what is anomaly or not. But in most situations where anomaly detection is actually important, you actually don't have these labels. And then you might want to resort to maybe some unsupervised method and use some clustering technique. But actually, in most cases where you find applications for anomaly detection, it's when you have a little bit more information. So you have a lot of label data on what is considered normal, but you have very little, almost nothing, on what you consider abnormal. So think about aircraft engines. So the ones which are working well, that's on planes right now, which some of you took in coming here. These are normal, but hopefully you don't have a lot of information on the features that gives you aircraft engines that crash the plane, right? So in these kinds of cases we can do semi-supervised, so it's sort of half labeled and half not, right? So it either belongs to this class or it doesn't. So, but our motivation, what we like to do is to just to take the simplest kind of non-trivial case where machine learning is useful in anomaly detection algorithms, and try and find sort of the easiest quantum extension to these. And what we do is that we choose the simplest type of anomalies are point anomalies, and the most useful kinds of cases are the semi-supervised regime, which I spoke of before. And in classical machine learning, there are two very popular algorithms for these type of problems. And these are based on the principal component analysis, and one class are SVM. So what I'll be talking about briefly is just quantum extension to these problems, but finding anomalies in quantum states. Okay, so just a little bit of motivation, right? So if we didn't know anything about anomaly detection, how would we go about finding an algorithm ourselves? So like a most naive way, we have a bunch of points, which we call normal. And then we have a piece of test data. We say, does this point kind of belong to these other points? Well, then the easiest thing you do, okay, well, what is the distance between this point and maybe the center of your other points? Okay, and this is very good. And then we just simply take this distance measure, and if it's larger than what we like, then we say, okay, it looks anomalous. If it's small, then okay, then maybe it's non-anomalous. But actually, we also need to take into account the distribution of the normal test data. So as an example, we have two cases, A and B, where the distance between the test point and the centroid are the same, but actually the distributions about the center are different. So in case A, we see that the blue point kind of looks a bit far. So we say, well, maybe this is an anomaly. But in case B, well, the blue point kind of looks like it belongs to the other green points. So we say it's normal. So this suggests we need to take into account the variance of our data about our centroid. And we take this account by using our covariance matrix. So here, and here our proximity measure, so sort of our improved distance measure, would be the total distance between our test data and the centroid, and you take away something like the maximum variance about the direction between the blue point and the red point here. And already we sort of see, here, we have an inner product here, and we know that quantum mechanics is, or quantum computers are better at sort of computing these inner products, so that's clue number one. And the second algorithm is one-class support vector machine. So we've all heard of two-class support vector machines, distinguishing between cats and dogs, and finding a hyperplane that somehow that best describes your data. So here we have a bunch of data in our feature space, which we say these are normal points. And we perform an extremization problem. So we find a hyperplane that maximally separates the distance between the normal points and the origin of the feature space, but minimizes the error about the hyperplane. And then we have our test data. And then our proximity measure would be the distance between our test datum and this hyperplane. And then this would be our new proximity measure. And here alpha is the Lagrange multipliers associated with the extremization problem. And then how do we solve? Really, our Lagrange multipliers are the only unknowns, and we know involves a matrix inversion problem. And here we have another clue. Okay, well we know classically matrix inversion is polynomial in M, the number of training data. But we know in the quantum case we can have an improvement in that, right, for solving matrix inversion problems. Right, so that's clue number two. So now I've just spoken about everything classically. What is the quantum problem? And the quantum problem is the following. We have M training states of dimension D, and we imagine some machine that outputs these states. And we're not given a description of what this machine is. We just know that maybe it varies a little bit from day 1 to day 2. And the output states of that machine, as it varies from day 1 to day 2, we still consider it normal. Like there's no large deviation between the different days. But it may be once we're given a test state. This test state, we don't know if it comes from that machine as it varies from day to day. It could be from a completely different machine. So our question is this new state similar to the states which we said are normal or not? Well, we can solve this when we say, well, let's solve this using classical machine learning. Okay, we can always do that. But what happens when we do that is that we need to convert the quantum information first into classical information. And to do that, we know we need some kind of tomography. And we all know how resource-intensive tomography is. So we want to avoid this as much as possible. So with state tomography, the number of resources would scale a polynomial in D, maximum D squared resources. So coming back to the original motivation, to solve quantum problems, using classical problems, because it requires this tomography kind of step, it's maybe more natural than to use a quantum algorithm where the initial input to the computer is originally a quantum state. So what we do is that we extend the principal component analysis and one-class SVM algorithms into the quantum regime. And we find a total of 6 different algorithms. So one that applies to pure states, or one set that applies to pure states, and another set that applies to mixed states. And we see we get an improvement in all cases relative to D, the dimensionality of the states, which is something that we desire in the first place because the bad scaling is with respect to dimension, if you want to compare to tomography. But also if we use some other quantum resources, we can also have an improvement with respect to M, which is the number of training states that we get. I'm not sure how long I have on OK, but in the interest of time, I'm just going to speak briefly about 2 of them, just the simplest 2. So I'm not going to have a lot of details here, but please come up to me afterwards for details. So we have the pure state PCA algorithm. So this is these states which we label as normal, and the test data that we want to ask, is this a normal state or not? And then we can similarly define, the equivalent of, the centered states. And the proximity measure that if we translate into a quantum language, it can be, so this would be the corresponding covariance matrix, which convert into a quantum state that we can create. And in the end, the circuit that, so the proximity measure would end up being a fidelity measure between this covariance matrix, which is a density matrix, and the centered state corresponding to the test data. And then we use something called a swap test, which is well known in a lot of these quantum machine learning algorithms, which basically is able to find the overlaps between two input states. So here our input states are the covariance matrix and the centered test datum. And these we can create using log m resources. And then, and this is a Hadamard and a controlled swap. And at the end, we make a measurement, a sigma z measurement. And here we can find the probability in which we get a 1 or a 0. And we find the probability to which we get a 1, 0 is then dependent on the overlap between the covariance matrix, density matrix and the center test state. And in total here, then we see we get sort of an advantage in both the number of training data, which we get from the method of creating the input states, as well as the dimensionality. And just another example, like a very simple mixed state one class support vector machine algorithm. So our normal data are now the mixed states, and our next test datum is also a mixed state. And then we have a modified proximity measure. So instead of the fidelity between pure states, we have a fidelity measure for mixed states, which we choose to be the super fidelity. And again, you can apply the same swap test mechanism I showed earlier, and get this particular advantage, where it scales logarithmically in the dimensionality, but we don't recover the same advantage for the number of training states. So there are 4 other algorithms, which I won't mention, but they basically have this pattern. There's always this improvement in dimensionality, but not always for the number of training states. And there are a lot of really interesting open questions here, because anomaly detection itself is, it's a very big field, and there are a lot of interesting things that we want to learn about quantum states. A lot of experiments that we're making. Sometimes we're not, completely sure of the states we're creating, or maybe we're looking for new patterns in quantum states that we might not be expecting. And there are, a lot of unexplored algorithms, because we don't know what kinds of algorithms are good for what kinds of quantum anomalies that we're interested in. So here we just have an example, but what I haven't provided is sort of a real life example. For example, this is good for finding entangled states versus non-entangled states, for example. And this can also be extended to anomaly localization algorithms. So classically, there's a problem like in networks where you want to find the origin of defects in your network. So this is an extension, and also the relationship between machine learning type techniques and state discrimination type techniques that Raman and Gael talked about. Yes. So this is more of a teaser. I don't really have much detail here. So please come and talk to me afterwards, and I'll love to discuss with you. Thank you.
Thanks, Nave. So, first question.
I very much enjoyed your talk. Thank you.
Thank you.
Given the work you're doing, what is your intuition about 2 things that plague commercial anomaly detection systems, for instance, in networking, which are twofold? One is establishing a good baseline for all subsequent measures. In networking, frequently your baseline is corrupted to begin with, and people want better baselines. And then the second related one is the problem that environments are frequently very dynamic, and you have a moving baseline problem.
Yeah, so maybe I'll go to the second question first. So in the second question, I understand it's more of like an online setting. So you have very like a time series type of data. Yeah, so in that kind of case, I mean, I don't see like an immediate advantage that the quantum case can have, because I mean the quantum case mainly has advantage because you can perform operations sort of coherently. But if you have sort of things which are more dynamical that come in, then then in principle you can imagine like a quantum operation that maybe coherently be applied across. But then there's a trade-off between resources. I mean, are you spending too much on that quantum resource, and what are you getting out of that? So I mean, we're thinking about it, but at the moment I'm a bit skeptical.
Okay, any other question? I have a question. Have you related your work to error correction? In the sense that if you let's say you can have, it's like your algorithm is searching for a defect that can be corrected later.
Yeah, so I'm going to discuss with somebody about error correction. Right? Yeah, it's we're thinking about it. Yes, but I don't have anything to say right now about it.
I will write the paper before you. Great, thanks, Anna, again.
Thank you.